Today's lecture is about exponential functions. Let's start with the definition of exponential function. An exponential function is a function where the variable is in the exponent. The general form looks like this. We have f of x or y equal b to the x, where b has to be either greater than 0 and it cannot be 1. Right? So on the number line, it looks like this. Negative infinity to positive infinity. Here is 0, here is 1. We do not want to be 0 or 1, but we can take things in between. We can take things in between. And so either between 0 and 1, or skip 1 and then from 1 to infinity. Okay. It cannot be 1 because if it was 1, then 1 to the x would be just always be 1, right? That's not very interesting. So it has to be between 0 and 1 and 1 to infinity. As you can see, you see two regions here. This blue region is called exponential decay. And then in the green region, it's called exponential growth. That's where the graphs grow. The domain and range of exponential function, the domain is going to be, let me tell you now, and I'll show you why later. So negative infinity to positive infinity, that's the domain. And the range is going to be from 0 to infinity. And this one, of course, applied to y equal b to the x. If you add, if you do some translation, move left, move right, or move up, down, or flipping, then the range will be changing, right? But right now, the domain and range will be applied to that function there, the parent function. All right, let's take a look at the case 1, exponential growth, where f of x equal b to the x and b is greater than 1. So we're talking about the green case here. Let me show you how just a graph and a table looks on decimals. We won't do it by hand though. Okay. Right here it is. And let me plot some points. There you go. When x equals 0. The one that I actually want to focus here is when x equals 0, y is 1. Because this is where everything starting. We're gonna start at this point. We're gonna move the graph. Okay, we don't start at 0, 0 like in quadratic function. We start at 0, 1 in the exponential function. Okay, so you can see from left to right, the function is steadily grow. Right, that's why we call it exponential growth. At a certain point, it grow really, really fast, really quick. Right? This represent say your retirement saving, right? You've been saving your whole life, and then when you say like 60, assume that you've been saving for like 40 or 50 years, then boom, look at that. The last few years of your retirement, you should get something like this. It's, hopefully, it should, if you don't, being consistent and whatnot. Okay. All right. Let me go back and draw on the lecture note. Here it is. All right, here's a graph. Now I want to mention that the standard form of the function, exponential function, is y equal 2 to the x minus h plus k. Right. So here in this case, you can see it is 2 to the x minus 0 plus 0. Right. It's kind of missing those two components. What is h and what is k? That will be your I don't want to call it vertex, your new point of the graph. So when y equal 2 to the x, remember what I say is that the point that I want to emphasize is this one right here, the one in red right there, from 0, 1. That's where we're gonna move your graph, right? The Hanazano asymptote here is going to be y equal, let me use purple here, y equals 0, and I'll show you where you're going to get that from. And y equals 0. Y equals 0. That's the Hanazano asymptote. Okay, that's the Hanazano asymptote. This component determines your Hanazano asymptote. Okay. All right. Case 2, exponential decay, where b is between 0 and 1. This little green blue part here. So if I have g of x equal 1/2 to the x, so b is 0.5 between 0 and 1, right? A lot of time you're gonna see people see me writing 2 to the negative x. Okay, that you know that it's gonna be a decaying case. All right, let me show you how it looks on decimals. It is. There you go. Again, when x equals 0, even in this case, when x equals 0, y is 1. And again, that would be our focus point. Okay. Let me go back and graph it on the lecture note. Right, there it is. And again, I want to emphasize, we're gonna focus on 0, 1. The Hanazano asymptote here is still y equals 0. I know one more thing, the black graph should not touch the x-axis. I know I'm trying very hard not to touch it. If you accidentally draw it touching it on your homework or exam, that's fine as long as you don't cross the Hanazano asymptote. Okay. Now, is there a better way to graph this without plotting? Because it's quite a lot of work. We don't want to do this all the time, right? Well, the answer there, yes, there it is. Right? So the answer is yes. Thank goodness. Right? So the standard exponential function looks like this. I kind of wrote it before on number 1, where the h component is gonna move sideways. Let me highlight that. So here the h component is gonna move sideways. It's horizontal shift. And again, if it minus h, you're gonna move right, plus h, you move left. Let me put that down there. Minus h, move right, plus h, move left. Plus k is the vertical shift. And it's pretty straightforward. If it plus k move up, minus k move down. It's also the Hanazano asymptote. Maybe I All right, let's graph this problem here. Y equal 2 to the x plus 2 minus 3. The first part will be determine the domain. For exponential function, domain is always all real numbers. So without even thinking, just write out negative infinity, comma, positive infinity. Right. As you can see in the graph earlier, right, either decay or growth. The Hanazano asymptote, HA here, is this component, right? And I do recommend you determine and graph the Hanazano asymptote before you even think about graphing the graph. Okay? So y equal minus 3 is the horizontal line, so it should be y equal. If it vertical line, it's going to be x equal. Intercept. So I'm going to set x equals 0. Y-intercept is when x equals 0. So y equal 2 to the 0 plus 2 minus 3 down here. That'll be 2 squared minus 3. That'll be 1. Okay, so 0, 1. Oh, all right. It's kind of coincident. Okay. It's coincident to the point that we actually want to focus on. The range is going to be later. The range has to be after the graph, right? So first of all, this is the exponential growth, right? First of all, we're going to determine its exponential growth. So its parent graph, the basic graph, it looks like this. 0, 1 there. That's, important point. So that's where we're going to move thing, okay? So that is my basic graph. Horizontal asymptote will be y equal -3. Gonna do dash line here, but we're not supposed to see it. It's just something that we, determine where the graph should hovering above to, so we don't draw it all the way down to the negative infinity. And then from this red dot, we're gonna move what? Let's see how we're gonna shift thing. X plus 2. So remember, if h is plus h, you're gonna move left. So this implies I'm gonna move left 2 unit, and -3 mean you move down 3 unit. Okay. So from that red dot, big red dot, we're gonna move left 2 unit, 1, 2, and then 1, 2, 3. So the new point is right there. Copy and paste. Make sure you don't cross the purple line. The y-intercept is 0, 1, 2. So make sure you cross that. So the new point will be -2, -2, -2. Okay. And that's how I want you to present your graph. Now the range, remember, if the domain is all the x value, then the range is going to be all the y value. So we look at the y-axis. Basically, you look at the height of the graph, how low and how high it goes, right? So from bottom top, where does it start? Well, it looks like it starts from -3. Of course, we don't include -3. We just kind of hovering above it. So we use parentheses and go to infinity. So that will be your range. So range will be the last thing. You got to graph first to see how high or how low the graph is. Okay, let's graph y equal 1/5 to the x minus 1 plus 2 using translation. Now this one I can rewrite it like this. 5 to the negative x minus 1 plus 2 with the same way of writing things. Okay. Domain is going to be from -infinity to +infinity. That's always true for exponential function. The horizontal asymptote is this component here, y equal 2. The y-intercept will be when we set x equals 0, then y equal 5 to the -0 minus 1 plus 2, so that'll be 5 plus 2 is 7. So 0, 7, 7, that'll be my y-intercept. Range will be later. Now this is the exponential decay. So your basic graph, your parent graph looks like this. Something like that. All right, something like that. Okay. You don't have to draw it there. I just want to put it there so you can see. It's not more like a guideline. So our shifting will be like this. The -1 tell me to move right 1, and then the 2 tell me to go up 2. That's all. Okay. So move to the right 1 and up 2. Right there. Oops, let me draw the horizontal asymptote 2, y equal 2. In my graph right there. 0, 7, that's my minus up. Okay. Make sure you don't cross that purple line. The new point will be 1, 3. Make sure you show me that new point. And the range, you can see from bottom top, where does it start? It starts at somewhere near 2, right? And to infinity. Okay. Let's take a look at the application of exponential function. Compound interest formula. These two formula will be given to you. Today we're going to focus on this one, right? We'll talk about this one later. Next time. So this is the compound interest formula where A is a current amount, your balance, your balance in your bank. P is the initial amount, how much you put in. R is rate, and make sure you always change to decimal. Yes, to calculate anything. T is time, usually it's going to be in year, right? And N is the number of compounding. So for example, no, e.g. For example, if it compound yearly, it's going to be N is going to be 1. Right? If it monthly, N is going to be 12. This is 12 months a year. Right? Quarterly, what do you think N is? How many quarters a year? 4. Right? If it's semi-annually, it'll be 2. So you get the idea. In April 2023, Apple announced Federal account service by Goldman Sachs Bank was available to customers. Penelope, who is an iPhone user, received a total of $1,500 in money gift on her 18th birthday from relatives. She decided to invest the money in the Apple saving account with interest rate of 4.15%. I believe it's kind of going down to 3.65 now. How much interest amount will Penelope earn in 4 years? Round to the nearest cent. So so let's see what we have. So that is my interest rate. And of course, I got to change it into decimal. So we R, so that's my R. Equal 0.0415. So they asked me for the balance, yeah? They asked me for the current amount. So I need principal. What's the principal? That is my principal, P. Right. What else? I need time. How many time? 4 years. So that's T. And what is the numbers of compoundings? I didn't give it to you. Apple compounded. They give you the interest money each month, so they compound monthly. So N equal 12. My bad. I should give it to you. Okay. All right, let's plug it in and calculate. A equal P1 plus R over N to the NT. So P is 1,500. 1 plus 0.0415 divided by 12, and then 12 times 4. Let me give you a happy ending. That would be 1,770, and always round to the nearest cent because we talk about money here. That's how much you got after 4 years. Okay, not a lot. All right. Now I know that we're going to talk about this formula later, but let me tell you right now when to use which. If you hear the word compound, like annually, compound, quarterly, compound, monthly, you're going to use this big long one, the bigger formula. If you hear continuously, you're going to use PERT, right? So this one is continuously. So basically, they press the end of keys like every single second. So we'll talk about that later. All right, one last one. Find the initial deposit. Oh, first thing first, they're looking for P, right? So it's initial deposit of an account that worth 14,472 and 74 cents. So this one is right now. That's how much it worth. That is A. That is my current amount after earning 5.5. Rate is 0.055. Compound monthly. So N equal 12 again. It's not always 12. For 5 years. Oops. 5 years. T equal 5. Round to the nearest dollar. Okay. Let's plug it in. Right. Let me write down. Equal P1 plus R over N to the NT. So A is 14,472.74. P is what we're looking for. 1 plus rate 0.055 divided by 12 to the 12 times 5. Okay. All right. Let me do it slowly so for the sake of the note here. So let's calculate that one first, and that will give you 1.3157 something equal the left hand side. Okay. And you divide both sides by 1.3157 something, get P. So P is roughly, after I done that, P is roughly 11,000. So the initial deposit was 11,000. Make sure you have unit, currency unit. Okay.